This is our first module for Math 211. We'll be talking about sets and numbers, the basic notation for those two things, and the assumptions that we will be making throughout the course. So the basic terminology and notation for sets. A set is a collection of objects, and the words collection, family, or class are used as synonyms for the word set. So if we have a set capital A and X is one of the objects in A, then we say X is an element of A, and the shorthand notation for that is this symbolism X, this symbol that looks like a Greek epsilon A. This is read X is an element of A. And if X is not one of the objects in A, if it's not an element of A, then the symbolism that we use is the is an element of symbol with a slash through it. Just like when you put a slash through an equality symbol, the meaning is not equal to. If we have two sets A and B, and every element of A is an element of B, in other words, you can get A from B by deleting 0 or more elements. Under these circumstances, we say that A is a subset of B. And the shorthand notation for this is this sideways U with a line under it. This is read A. A is a subset of B. And we will look at some examples as soon as we look at a little bit more notation for set theory. Okay, so we're going to talk about ways of describing sets, and one way is known as the listing method. The listing method for describing a set is simply to list the elements between braces. So for example, we could let capital A be the set whose elements are 1, 2, 7, and 32. Sort of a random example of a set described by the listing method. So for this set, we know that 1 is an element of A, 2 is an element of A, 7 and 32 are elements of A, and no other object is an element of A. And it is possible, if we wanted to rewrite the sentence, X is an element of A, for this particular A, without using any set notation, and here's how we would do it. X is an element of A is equivalent to saying X equals 1, or X equals 2, or X equals 7, or X equals 32. We might have to do this in some of our proofs that will be coming up later in the course. So the listing method works pretty well for small finite sets, but for large finite sets it's really impractical, and for infinite sets it's really impossible to use the listing method as it's just been described. So here are two examples of some variations of the listing method for describing either large finite sets or infinite sets. So here the set capital A consists of the numbers 1, 2, 3. The three dots are read either and so on, or they could be read continue the pattern that's been established until you reach 107. So the set notation here on the right, this variation of the listing method, is intended to describe the positive integers, the positive whole numbers from 1 through 107. Here's an example of an infinite set described by a variation of the listing method. This is pretty similar to the previous variation. So B is the set consisting of the numbers 2, 4, 6, and so on. And in this case, the three dots can be read and so on, or they could be read continue the pattern established forever. So B is the infinite set consisting of the even positive integers. So one of the problems with either of these two methods is that it's either impractical in the case of large finite sets or impossible in the case of infinite sets to rewrite the statements x is an element of A or x is an element of B without the use of set notation. Okay, look at a couple more examples. Here's the variation of the listing method we just discussed. Capital boldface N is the set consisting of the integers 0, 1, 2, 3, and so on. This is called the set of natural numbers. The natural numbers are the positive integers, positive whole numbers, and 0. The standard symbol for the set of integers is this capital boldface Z, and here's yet another variation of the listing method. You could think of these three dots as meaning continue the pattern forever to the left, and these three dots mean continue the pattern that's been established forever to the right. So this is the set of integers, what we ordinarily think of as whole numbers. Okay, there is another method for describing sets, a method different from the listing method, known as the rule method. And when you use the rule method, we use braces. We use a variable, and we'll be using the variable x in most of our examples. You use a set which is already defined, and in our theoretical discussion of how this works, we will use capital A, thinking of capital A as being a set which has already been defined. And then you also need a sentence that has as part of it the variable x. So suppose P of x is a sentence in which the variable x occurs. We'll look at some examples shortly. Then the set whose elements are the objects in A for which P of A is true. The objects in A for which P of A is true is denoted like this. So this is read the set of x's in A. The colon is read such that, so the set of x's in A such that P of x. Or the other possibility is to replace the colon by a vertical line segment. The vertical line segment is also read such that. And P of A, P of A is supposed to be the result of replacing x by A in the sentence P. So if you've probably seen this before, but if not, I think things will be a lot clearer once we look at an example. which we have here. So capital A is the set of little x's, x's in capital Z, the set of integers, little x, such that x squared is greater than 100. So the P of x, the sentence in which x occurs in this case, is the mathematical sentence x squared is greater than 100. So for example, taking the number 17, P of 17 is the sentence you get by replacing x in P of x, replacing x by 17. P of 17 is the sentence 17 squared is greater than 100. This happens to be a true sentence. P of 17 is true, and 17 is an integer, so 17 is in A. Second example, the set of even positive integers could be written like this. The set of n in the set of integers such that for some positive integer k, n is equal to 2 times k. So this is a way of describing the set of even positive integers. Let's see, I have used the variable n here instead of x. Sometimes it will be good to know how to translate membership in a set given by the rule method to a statement that doesn't involve any set notation. This is not hard to do. Saying that little a is an element of the set of x's in capital A such that P of x is the same as saying that x is in A and P of A. Right? When we say that A is an element of this set, we're saying that AA is one of the x's described here. A is in capital A, and the sentence P is true when you replace x by A. So looking at the set we looked at before, the set of even positive integers, the sentence A is an element of the set of little n's in the set of integers such that for some positive integer k, n equals 2k, is the same as saying, we're saying little a is one of these n's. So what we're saying is that a is an integer, and for some positive integer k, a is equal to 2k. Okay, so here are a couple more examples which sort of use the rule method. Capital boldface Q. This is known as the set of rational numbers. These are the fractions whose numerator and denominator are integers, and you have to make sure that the denominator is not 0. So capital boldface Q, the set of rational numbers, is all numbers of the form a over b, such that a and b are integers, and b is not equal to 0. So as I said, capital boldface Q is the set of rational numbers. It's easy to come up with examples of rational numbers. Just take the quotient of two integers, 7/12, is a rational number. Minus 302 over 17, 21 over 47, these are pretty much random choices. 17 is a rational number because 17 is the quotient of two integers. 17 is 17 over 1. And then the second of these two examples is this capital boldface R, the set of real numbers. I'm going to describe the set of real numbers like this. These are numbers that can be represented by points on a number line. I haven't really used set notation here, and to actually describe the set of real numbers is not easy. But these are the numbers that you work with in algebra and calculus. What you usually think of when you think of a number. Some examples of real numbers, well, these are easy to come up with also. 3 is a real number. 45/11 is a real number. Square root of 2 is a real number. Pi is a real number. So our description of the rational numbers is not quite what the rule method requires, right? Here was our description. The set of numbers of the form a over b, where a and b were integers and b not equal to 0. Whoops, I left off a right brace here. But it is possible to rewrite this description of the rational numbers like this. It's the set of x's such that x is equal to a over b for some integers a and b is not equal to 0. So I could put this in the standard rule method form if I needed to. So here are three sets of numbers that we've talked about so far: the natural numbers, the integers, the rational numbers, and the real numbers. So I just wanted to note on this slide that every natural number is an integer, right? Every one of these is one of these. Every integer is a rational number. And every rational number is a real number. So using the subset notation, we could write those three sentences in a shorter form. The set of natural numbers is a subset of the set of integers, is a subset of the set of rational numbers, is a subset of the set of real numbers. And in addition to the symbols capital boldface Z, Q, and R, we will put a superscript plus on those symbols to mean the set of positive numbers in that set. So Z plus, Q plus, and R plus denote the positive integers, the positive rational numbers, and the positive real numbers, respectively. So, for example, capital boldface Z plus is equal to the set 1, 2, 3, 4, and so on. Okay, so in any math course, you need to have some starting point. You can't start from the very beginning. In a calculus course, you assume things you learn in an algebra course. And in this course, we will be making some assumptions about things we know. and things we can use. So we will be assuming all the mathematical facts about numbers that you're likely to learn in a college algebra course. I've got some examples here on the slide, but this is not an exhaustive list. Basically, anything you learn about numbers in algebra, you can use in this course. So there are the algebraic identities, simple things like x plus y is y plus x for all real numbers. This is the commutative law for addition. You may have heard that name. The commutative law for multiplication, x times y is y times x, for all real numbers x and y. The associative law for addition. If you're adding three numbers, x, y, and z, in that order, you can add the y and the z first and then add x. Or you can add the y and the x and the y first and then add z. Here's the law for squaring a binomial, which you probably know. We'll feel free to use things like this. The distributive laws. X times the quantity y plus z is x times y plus x times z, which we would usually write as xy plus xz, using the usual conventions for omitting parentheses. Right? The usual conventions are that when there are no parentheses, you do multiplications before additions. We will be assuming the properties of inequalities that you probably learned. Here are some examples for all real numbers x, y, z, and w. If x is less than y and y is less than z, then x is less than z. This is called the transitive law for less than. If x is less than y, then x plus z is less than y plus z. In other words, you can add any number to both sides of a true inequality and it will remain true. If x is less than y and z is less than w, then x plus z is less than y plus w. You can add two inequalities. If x is positive and y is less than z is true, then you can multiply both sides of this inequality by x, and the resulting inequality will still be true. You can multiply both sides of an inequality by a positive number, and the inequality will remain true. And as you probably know, if you multiply both sides of an inequality by a negative number, the inequality is reversed. That's the contents of number 5 in this list. Given two numbers, x and y, exactly one of these three things will happen. Either x is less than y or y is less than x. And the third possibility is x equals y. And finally, a property involving absolute values. This may be less familiar than the others. You can rewrite an inequality involving absolute values, an inequality of this form, in this way. The absolute value of x is less than y has the same meaning as x is between minus y and y. When this comes up later in the course, we'll talk more about it. And then there are corresponding properties for greater than, less than or equal to, and greater than or equal to. And now here are some properties that you probably know are true, but which will play a bigger role in this course than in your previous courses. The closure properties. You may not know them by this name, by the name closure properties, but I think they will be at least sort of familiar. Okay, so let's list a few of the closure properties. The first one is for all real numbers x and y, x plus y is a real number. And I see here that I have used this symbol, this capital upside down A, which I haven't talked about. This is shorthand for the word for all, or for every. We'll talk about this in more detail later. So this sentence says for every pair of real numbers x and y, x plus y is a real number. And this formula is usually expressed by saying that the real numbers are closed under addition. Right? Saying the real numbers are closed under addition means that if you add two real numbers, you get a real number. The real numbers are closed under multiplication means that for all real numbers x and y, x times y is a real number. Saying the real numbers are closed under multiplication means if you multiply two real numbers, the result is a real number. And here are some closure facts that we will be using. The real numbers are closed under, well, addition, multiplication, as we've seen, and they're closed under subtraction. If you subtract two real numbers, the result will be a real number. The real numbers are not closed under division. It's not always true that if you divide two real numbers, the result will be a real number, because dividing by the real number 0 does not give you a real number answer. But it is true that for all real numbers x and y, as long as y is not equal to 0, x over y is a real number. So the real numbers are almost closed under division, but not quite. And sort of a similar thing for square roots. If you take the square root of a real number, you may not get a real number. You won't get a real number if the real number whose square root you're taking is negative. But as long as x is greater than or equal to 0, then the square root of x is a real number. The rational numbers, these, remember, are the fractions. The set capital boldface Q. The fractions whose numerator and denominator are integers. They are closed under addition, multiplication, subtraction. If you add, multiply, or subtract two rational numbers, you get a rational number. And the same kind of thing holds for division, which held for the real numbers. If you divide two rational numbers, as long as you're not dividing by 0, the result is a rational number. Okay, what about the integers? Remember, these are the positive whole numbers, 0, and their negatives. Capital boldface Z, under which operations are the integers closed? Well, if you add two integers, you get an integer. And if you subtract two integers, you get an integer. And if you multiply two integers, you get an integer. Addition, multiplication, and subtraction. The natural numbers. So remember, the natural numbers are the positive integers together with 0. If you add two natural numbers, you get a natural number. If you multiply two natural numbers, you get a natural number. But if you subtract two natural numbers, you don't always get a natural number. They are not closed under subtraction. Just addition and multiplication of the operations that we've talked about here. Okay, so here's sort of a sample question. Under which of the operations, addition, subtraction, multiplication, and division, is the set of positive real numbers closed? This would be the set capital boldface R superscript plus. Well, the sum of two positive real numbers is always a positive real number, so the positive real numbers are closed under addition. Sorry about that little jump there. What about the operation of subtraction? If x and y are positive real numbers, x minus y may not be a positive real number. If y is larger than x, it won't be. So the set of positive real numbers is not closed under subtraction. However, multiplying two positive real numbers always gives you a positive real number. So the positive real numbers are closed under multiplication. And similarly for division. If you divide two positive real numbers, the result will always be a positive real number. No problem with dividing by 0 here, because 0 is not positive. Therefore, the set of positive real numbers is closed under division.